All right, so today we're going to be learning how to use these Texas Instrument calculators, which we're going to be using in class here. Now, if you happen to know how to use a calculator already, you probably don't need to watch this video, but there was a lot of confusion, last semester on how to use a calculator, so that's why I'm making this video. So hopefully there won't be any more undue confusion on, something that you really should have been taught back in grade school. But apparently, I guess they're not teaching this stuff anymore. So we'll be going over these types of calculators. So this is a solar calculator, as by the nice little solar panel on the top there. So there's no battery in here, so you don't have to worry about turning these things on or off. Of course, always when you use these things for the first time, you just want to press the on button, just make sure it's cleared, because sometimes there's some weird memory corruption in there when it hasn't been used for a while. So we're going to go over a couple examples here, so hopefully it'll be a little bit familiar to you. We'll also do basically a day just playing around with these calculators, so when the exam comes up, you're not completely confused by these things here. All right, now for some examples. So let's say we want to use the negative sign, so we want to make something negative, so then you just would hit like 5 negative. That obviously just makes it negative, and if you happen to hit it accidentally, you want the negative to go away, you just hit that again. So you can very easily just make it negative. Now let's say we want to take negative 5 plus 3. So you go 5 and with the plus minus, then add 3 to that, hit the equal sign, and you get negative 2, unsurprisingly enough. For the next one, we're going to be dividing. So we have here 5 divided by 2 plus 3. Now, written out, you can obviously see that's going to be 5 divided by 5, so you should get the answer of 1. Now, when we're doing this, we are going to be using up here these little parentheses, right? Because we want to make sure when we're dividing that, the 2 plus 3 stays on the bottom, and we don't go there and say 5 divided by 2 and then plus 3, because we'll get a very different answer. So here, there'll be 5 divided by, then using the parenthesis, 2 plus 3. You close the parenthesis, that's going to tell you a 5, because 2 plus 3 is 5. And then you hit the equal sign, so that's going to be 5 divided by 5, which of course is going to be equal to 1. And you can very easily see how this could be very different if you want 5 divided by 2, then plus 3 to give you 5.5, which is obviously very different from the original answer we had, and works out to be something very different. So again, just be very cautious of that. And the next one, we have here 5 divided by 2 times 3. So you go here 2 times 3, which is going to be 6, obviously. So then you're going to get 5 6, or 0.833333. Again, that'd be very different than going here 5 divided by 2 times 3, which gives you 7.5. Obviously the wrong answer, because that's going to be 15 divided by 2, which is very different. The other way you could also do that is simply by recognizing that, 5 divided by 2, and then you're also dividing by 3. So 5 divided by 2, and then dividing by 3, you get again that 5 6, or 0.833333. All right, for this next example here, we're going to have a negative 7 plus 3 in the numerator, and then 8 times 4 in the denominator. So again, starting our parenthesis, we're going to have negative 7 plus 3, close the parenthesis, which of course is negative 4. Then you go here and divide that by 8 times 4. Close the parenthesis. 8 times 4 is of course 32. Hit the equal sign and we get negative 1/8, which works out to be a negative 0.125. So again, whenever you're dealing with stuff in the numerator and denominator, especially if you're adding, subtracting, multiplying, dividing, make sure to use your little parentheses. And worst case scenario, if you're just a little bit uncertain about what you should do, go there, calculate the numerator first, calculate the denominator first, and then just divide those two numbers. And again, that's just really a great way just to double check, because you can't always trust a calculator, especially if you enter the numbers wrong. All right, so the next one here, we have Avogadro's number. So as we'll be learning later on, this is the number of atoms or molecules in a mole of substance, and we're going to be seeing why this is so important. But anyway, this is one number you'll become very familiar with, 6.022 times 10 to the 23rd. All right, right here, this 23 with a little exponent up here, this is referring to that times 10 to the 23rd. So that's how you write it. You don't use any of these up here. You might be thinking, oh, there's that 10 to the x thing here on the log button. No, we're not going to be using the log or the the natural log, any stuff in our class here. So what we're going to be using here is instead this EE button. Okay, so this button you're going to become very familiar with. You're going to be using it a lot, and it's very, very useful. And this is going to be that 6.022 times 10 to the 23rd. That's what it's referring to right up there. So don't go there. Occasionally what some students will do, and this again is the wrong way, 6.022 and then multiply by 10 to the 23rd. Because this is 10 times 10 to the 23rd. So this is going to give us 6.022 times 10 to the 24th. That's wrong. So all you need to do is the 6.022, the EE, which refers to the times 10 to the, and then 23, and then you're done. Okay? Next up, we have Planck's constant. So this is, we'll be seeing this when we get to the quantum mechanics. So we have here Planck's constant, which is 6.626 times 10 to the negative 34. All right, so what this is referring to is again the 10 to the 34, but it's a negative sign now. So this is using your little plus minus key. And once you use the exponent, the plus minus is always going to just stay up here. So if I hit this a bunch of times, it just changes the sign up here. You can't actually do anything out in the front here with that. So if you want like a negative of this, either you enter your number then multiply by -1, or make sure that you put your negative sign in before you actually do that up there. All right, so here we have a little bit more complicated expression. We have here h times c over lambda, so it's Planck's constant times the speed of light over the wavelength of light, and we'll be seeing this later on when we calculate the energy of a photon of light. So very simply, here's our 6.626 times 10 to the negative 34, like we saw. Then we multiply this by the speed of light, which is 3 times 10 to the 8th. Then we divide that by the wavelength of the light we're interested in, which is going to be 520 nanometers, or 520 times 10 to the negative 9. All right. And then we simply just push enter, and we get a value of 3.82, and the rest, times 10 to the negative 19. And the units on this would actually be joules. Now, one thing you should have noticed is when I was entering these values, I very easily just went 520 times 10 to the minus 9. I didn't have to convert this into the scientific notation where it was 5.2 times 10 to the minus 7. You just can enter the value 520, and after a while that nano means times 10 to the minus 9, and then you can very easily just put up there that times 10 to the minus 9 without having to worry about moving your decimal place over, which in another video I explain can be a little problematic if you're not careful. All right, so next up we're going to be calculating the volume of a sphere, and the sphere is actually going to be the sun. So here we have 4/3 pi r cubed. So you should remember that from your geometry classes back in high school. What we're going to do here is essentially, and usually when we're dealing with equations like this, it's kind of better to start off with the exponent part, because sometimes if you happen to push the wrong key while you're doing these calculations, you might wind up cubing the entire thing rather than just the number you're interested in. So we're going to start first of all cubing the radius of our sun, which is 696.3 million meters. So 696.3 times 10 to the 6th, just like before. Then we want to cube it. So there's two ways we could do this. We have here this y to the x button, and also down here, which I don't know if is easy to see, but there's a x cubed button right on here. Don't know if this is showing up well. And if we have this little cubed button right here, we can do that. Although generally it's kind of just a good idea to use this y to the x button. It works pretty good because this one's kind of hidden down there in the bottom. You might miss it. So anyway, you just cube this. So you hit this button times 3. All right, well, this is mainly cubed. And then what you're going to do is just multiply that by pi. And it takes a few seconds. And then you're going to multiply that by the 4. Then divide that by the 3. And there's going to be our final answer, which for some weird reason works out to almost the square root of 2 times 10 to the 27th cubic meters in this case. So here we have 1.41, 1.41, blah, 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 times 10 to the plus 27 cubic meters. And again, the order that you put it in there is important. And if you happen to forget that you need right here, this little button here for cubing, worst case scenario, you just go here, 696.3 E6 times 696.3 times 10 to the 6th times 696.3 times 10 to the 6th. Essentially, we've just cubed it, times pi times 4 divided by 3, And we get, the exact same answer that we did before. So if you happen to forget, about this little button here for cubing things, or this one down here for cubing things, you just multiply it together 3 times. It's exactly the same value. All right, for this next one, we have a more complicated expression. We have 1 over lambda, and here lambda is the wavelength of this light that we have, is equal to r sub h, which is the Rydberg constant, times, and this is in parentheses, 1 over n1 squared minus 1 over n2 squared. These are the values that we're going to use for this particular equation. So Rydberg's constant, this is a value, 1.097 times 10 to the 7th. The unit is inverse meters. And then the n1 and n2 are just 2 integer values. All right, so n1 will just look as 2, and n2 will choose to be 3. These really can be any integer values. This formula right here is for calculating the wavelength of light in a transitions in a hydrogen atom. So something, again, we'll be seeing a little bit later on. So, again, this is a pretty complicated one. So how do we do this? Simply just do it piece by piece. So first of all, enter our Rydberg constant, 1.097 times 10 to the 7th. And then we multiply this, and we use our little parentheses, and then 2 squared inverse, which of course is just 1/4, minus 3 squared inverse, which is just 1/9. Close the parentheses, and that gives us this value. And then we just have to push the enter, so the value in parentheses is multiplied by my Rydberg constant. And we get this value, 1523611.111. And these units would be in inverse meters. Now, of course, the equation up here is 1 over lambda. So this is 1 over lambda, but we are interested in lambda, so we need to take the reciprocal of this answer. So we just hit the 1 over x key again. And we get this value over here, 0.000000656, and that would be in units of meters. This you could easily convert into scientific notation. You just have to count how many zeros it's over. But if you're doing this, it's kind of easy to goof it up, because if you happen to just count 1 0 off, if you're not careful. So what is nice little trick is using these buttons on the bottom here, which are for floating, scientific, and engineering. So you can see right here, floating, scientific, and engineering. So floating is the default, and this is going to display your answer like this, which is not always the most convenient. Scientific is when it's going to be displayed as a times 10 to the some number. And engineering is going to be displaying it as a times 10 to the some multiple of 3. So what we're going to do here is simply just look at this answer using the scientific. So it's very simply second scientific, and now it displays at 6.56 plus a whole bunch of other stuff which was off screen times 10 to the negative 7. All right, so that makes it a lot easier when you're trying to write down your answer in scientific notation instead of putting a billion zeros right in front of there. And also we can do this in the engineering notation. So notice this is 6.56 times 10 to the negative 7, but if we go here and put this in engineering notation, now this is going to be 656 times 10 to the negative 9. So this is always going to display it in multiples of 3, which is very convenient, because when you start looking at your SI prefixes, we have things like milli, which is 10 to the minus 3, micro, which is 10 to the minus 6, nano, which is 10 to the minus 9, pico, which is 10 to the minus 12, and so on. And so essentially we can look at this right now and say 656 nanometers, and it's just very easy instead of trying to move your decimal point around by 2 or 3 places, which can be a little bit inconvenient when you're doing it. All right, and just to show you that this does stay as 10 to the minus 9, if I divide this thing here by 10, this decimal place is going to move over by 1. So if I go here, divide by 10, notice it's now 65.6 times 10 to the minus 9. I divide by 10 again, it's now 6.56 times 10 to the minus 9. I divide by 10 again, and now it's 656 now times 10 to the minus 12. So it's always going to remain as a multiple of 3. So 3, 6, 9, 12, and so on. So again, if now I'll just go here and multiply by 10. So now we're at 6.56. Now we're at 65 times another 10. Now we're at 656. So now I multiply by 10 again, and this is going to now go to 10 to the minus 6. Right here, so it's now 6.56 times 10 to the minus 6. So again, it's very convenient when you're dealing with that. And if you want to go between the other conventions, you can very easily just hit the scientific or the floating point. In either way, it'll work out very nicely. And for our last example here, this is actually calculating the root mean square speed of gas molecules. So we have here 3RT over m. So R is this thing called the gas constant. T is going to be our temperature in Kelvin, and m is going to be the molecular weight in terms of kilograms per mole. So if we do this, it's going to be 3 times 8.3145, which is a gas constant, joules per mole Kelvin, times our temperature, which is going to be 300 Kelvin here. And then we simply go and divide this by the molecular weight of nitrogen in terms of kilograms, so 28 times 10 to the minus 3. Equal that out. Now we have to take the square root. Very easily, just use this little square root button. And it works out to be 516, well, rounded to 517 meters per second for that. All right, and I think that's basically all the examples we want to do for this. We'll just look at some of these other keys now. All right, so anyway, just pointing out, all these little keys here, and sorry about the shadowing. It's a little difficult to get good lighting on this without, it reflecting way too much here. So anyway, what we have here, of course, is our second key. If you need any of these yellow keys up on top there. Degree, minute, seconds, really, we won't be using that at all in this class. Log, base 10 or base E. We're not going to be using that at all in this class. You don't need to worry about that. The CEC, this is if you happen to make a boo-boo, and without wiping out, the entire problem, you could use this equate, use a little button here just to clear out part of your answer. So the hype, this is for your, hyperbolic trig functions. Again, not using any of that. We're not doing any stuff here with the trig functions, so don't worry about that. Again, this y to the x button, if you're dealing with this, very useful. If you want to cube something, raise it to the 4th, 5th power, or whatever. That's very useful. Above there would be the root of that. So if you want to take the cube root or the 4th root, the 5th root of something, that can actually be very useful. Pi, you should be familiar with that. We'll be using those. The 1 over x for taking your inverse. Again, that's very useful. The squared button, we'll be seeing that a bunch of times. The square root, we'll be seeing that as well. Then over here we have the sigma plus, sigma minus. Also here with these n's, sigma x squared. All these buttons over here, these are basically dealing with statistics, probabilities, the stuff up here, frequency, the average of x, the standard deviation. All this stuff is statistics and stuff. We're not going to be worrying about that. Over here we got that p to r, r to p, that's polar to rectangular coordinates. Again, not worrying about those things at all. Then down here, well, obviously our numbers that we'll be using. The floating scientific and engineering, like I pointed out earlier. Over here it also has a cube button. So if you want to cube something, you can actually just use this button over here instead of using the y to the x. But if you happen to forget it's there, you can use both of them. If you want to take percents of something, basically it just moves the decimal point over by 2. If you want to use that, that's fine. The factorial button, we won't be using that at all. Right here, this will be taking the cube root. Again, you could always just use this button over here. It's basically the same thing. And right here, this fix button. This is actually if you want to go and just fix the number of decimal places that you actually see on there. You can do that, but basically I never really use it that much. And of course, here's the plus minus button that we use. Over here, this is going from your angles, degrees, minutes, and seconds, so don't worry about that. Over here we have the storing and recalling of numbers. So actually if you're doing a long calculation, you're using, let's say, Planck's constant a bunch of times or Avogadro's number, and you don't feel like typing it in each and every time, you could always just store that in there and then just use a recall button to do that. But if you want to, great, but you don't really need to do that for these type of calculations here. All right, and then when you are done with the calculator and you are returning it, do not just plop the calculator in like this. The proper way is to take the calculator, flip it around, and fold it in, and now the calculator is properly put away. Okay, you have no idea how many times people will take the calculator and try stuffing it in this way, which is completely backwards and it doesn't fit. So what do? They try squishing it in even harder. No, that's not the way. All you do is you just put it like this, clicks in very nicely, should slide in, and really that's all you do. You just take it, slide it off, turn it around, and boom, you're done. You don't take it off this entire way, then flip it around 180, and then try squeezing it in there. I don't know why students do that, but that's really not what you have to do. So you just simply take it, fold it, boom, you're done. All right, then you simply just put it in the box from which it came. Again, you have no idea how hard students find that to actually be. And the number, is right on there, so you just have to look, match it up, and you're good to go. All right, and hopefully you found that useful, and we'll again have a little group work on this just so you get more familiar with the calculators, so when exam time comes around, you're not completely lost.